So, welcome to today's live interactive session or problem solving session, geology and soil mechanics. So, last week we had discussed problems on settlement calculation due to uh, mostly due to primary consolidation. So, we solved some of the numericals. First of all, we studied the concepts uh, from which then after that we derived the equation how the settlement of a clay layer can be actually consolidation settlement of a clay layer can be determined. So we solved a lot of problems in the previous class, and in today's class we will be mostly focusing on the uh, uh, 1D consolidation, one-dimensional consolidation theory. So which deals with the time rate of consolidation. It is how much time is required for a certain amount of consolidation to take place. Okay, so here till the previous till the sixth week, everything was limited up to the amount of consolidation, and now in this week we will be studying how much the time will be. The time factor will also be coming into the discussion. So where we will be seeing how we will be able to calculate how much time will be actually required for a certain amount of consolidation to take place. Okay, so first so in the beginning we will be thus revising some of the concepts of one-dimensional consolidation theory, and after that we will be solving some of the problems based upon that, and also we will be actually solving some problems on settlement also. Okay, settlement calculation. So let us start. So we had actually studied this E versus like the void ratio versus pressure plots. Okay, so as we know, as the effective pressure is actually increased, the void ratio comes down. Okay, so initial void ratio is E1, E naught. Then as we start putting the pressure on the soil, there is settlement. So due to this consolidation settlement, water in the pores actually gets expelled, and due to which there is a certain amount of settlement in the soil, and due to that settlement, the void ratio also reduces, right? So, as we can see here, as the effective pressure actually increases, our void ratio is decreasing. Cool. So here you can see a more elaborate void ratio versus effective pressure plot, where the loading is shown here. The loading, you can see the loading. So from A to C, it's actually the loading part, and then we have the unloading part, which is C to D. Okay, C to D is our unloading part, and then we have a reloading part. Reloading part is from D, F, G. That is our reloading part. So initially there was some void ratio. So what happens is that we keep on increasing the pressure, effective pressure. So up to the point C, we increase the effective pressure. So as we reach the point C, what we do is that we unload the soil. We keep on reducing the pressure. Okay. So we reduce the pressure up to this point. So you can see that initially in this at this effective pressure, there was certain amount of void ratio, say E1. Okay, but again when we are unloading it, we are reaching the same amount of effective pressure. So this value, the same amount of effective pressure. Now the void ratio is, we are not going back to that E1 position again, right? So there is some permanent kind of deformation. So we cannot reach that E1 again. We will be reaching a lower void ratio of E2. So after that, so this is actually known as the reloading, the unloading curve. Okay. Now again, what we start to do is that we start to reload it again. So this is my reloading curve, reloading. So what we do is that we again keep on increasing the pressure, right? So we keep on increasing the pressure. What happens is that you can see the reloading curve, this AFG curve or AF whatever this curve has a flatter slope than AC curve. Means the void ratio is not reducing at the same intensity, at the same slope as at the same intensity it actually like reduced before. So the slope is actually flatter. So AC has a steeper slope. The DFG has a flatter slope. Since DF has a flatter slope. Okay. So the main reason behind this is that the soil means the soil has actually encountered a stress when you are at when you are at this point in the loading. In his history, in his previous history, the soil has actually encountered a stress higher than that, right? In his history. So again, when you are reloading it, the soil will be not acting the same way, because it will say that okay, I have encountered a higher stress level before, so now you uh, cannot like affect me the same way as you affected me before. Okay, so the reloading curve actually has a flatter slope. Okay, so and after we cross this point, after this we cross this C point, the slope of the slope of this FG line is actually similar to this line, this portion of the curve. It means the slope is actually increasing, because as we cross this stress level, so now this these stresses are the stresses at these levels are actually the maximum pressures of stresses it has the soil has encountered in its history, right? So the slope will again keep on becoming steeper, right? Now what is my pre-consolidation pressure? The pre-consolidation pressure is nothing but maximum effective past pressure. Means in the past, a soil has the maximum amount of pressure that a soil has actually encountered. Okay. Okay. So when we are here, our pre-consolidation pressure was actually this thing, because in the past this much pressure the soil has already encountered. So this was our pre-consolidation pressure. Okay. Now, next thing which we study is how to determine this pre-consolidation pressure graphically. Because say you will be taking a soil sample from the field, say. So you will be taking a soil and you will be doing the one dimensional consolidation test in it, right? You will be doing the consolidation test. So you will be just getting a what results are you going to get from that consolidation test? You will be getting the void ratio versus the effective pressure plot. You will be able to draw that plot, right? You will just be able to draw that plot. Now, from that void ratio versus effective pressure plot, you need to determine our pre-consolidation. So Casagrande in 1936, Casagrande actually gave a graphical method using which we can determine the pre-consolidation pressure. Okay, so let us see what that graphical method is actually. So this is my void ratio versus effective pressure curve, which you will be getting by conducting a one-dimensional consolidation test. Okay, this you will be obtaining. Now, first of all, what you have to do is that you have to locate. Okay, you need to locate the point where where my uh, where the graph or the plot has maximum radius of curvature. Okay, just by visually you have to identify the point where the radius of curvature is actually maximum. So here see we have identified the point A as having the point having maximum radius of curvature. Okay, so what we do is that we draw a straight line parallel to my x-axis. Okay, AB. We draw the straight line at the point A. The point A has been visually identified as the point having the maximum radius of curvature. Okay, so what we do is that we draw a straight line parallel to our x-axis. Straight line is AB. right? Now, the next step is that what we do is that we draw a tangent AC at the point A. What we do is that we draw a tangent. Okay, we draw a tangent AC. Next, what we do is that now see, now we have an angle CAB. Okay, we have this angle. So what we need to do is that we need to bisect this angle. So what we do, we bisect, draw the angle bisector of this angle. So this AD is our angle bisector. AD is my angle bisector. Done. Now what we do is that in our curve, in this curve, we will see that here at towards the end, it will be almost a straight line. So here, similar to this, here you are getting almost a straight line, right? In the void ratio versus effective stress plot. Okay, a straight line. So what we do is that we extend this straight line backwards to intersect the line AD at F. Okay, it intersects the line. This line we extend backwards. It intersects the line AD at F. Then what we do is that we just find out the ordinate of this point F. Okay, ordinate. So not the ordinate, the abscissa means the x, this value, x value. So the abscissa of this point F, it is the x coordinate of this point, will actually give us the pre-consolidation pressure. Okay, so this is how you have to determine the pre-consolidation pressure graphically. Okay, I hope this is clear. Now these things we already solved some problems using these relations in the previous class. So we will just go through it very fast. Okay, just to revise, to brush up the things. So so say you have a car. Okay, okay, so let me try to. But this is my effective, sorry, this is my effective stress, and this is my void ratio. Okay, the log of log scale. Now this is my what? This is my pre-consolidation pressure. Okay, this is my pre-consolidation pressure. Now if see this is my initial stress, this is my initial stress. If after increment of stress, the new stress which is coming, which is this stress, this was my initial stress. After increment, this is my total stress, right? This is my effective stress. But if this stress is less than, means say initially you were here, okay, initially this was this, then you increase the stress, you came here, and this much is your this distance. Okay, so if this point, oh, okay, if this point is actually less than the pre-consolidation stress, that means our soil is over-consolidated in the over-consolidated region, and this is my normal consolidated region. This is my over-consolidated region. This is my soil is in the over-consolidated region. So what we need to do is that why in my settlement calculation equation, which is nothing but CSHY1 plus C naught log of the updated stress by the previous original stress. So here what you have to use is that you have to use CS, that is the slope of the rebound curve. We cannot use CC here. Okay, you cannot use CC here. It is we cannot use coefficient of curvature. Sorry, coefficient of this one compression index here. Okay, we cannot use compression index here. We have to use the slope of the rebound curve, which is C suffix S. Okay, this is the first case. The second case is that Second case is my initial stress was actually less than the pre-consolidation pressure, but my updated stress, the in this is my total input. Okay, so my incremented stress, this stress is actually greater than the pre-consolidation. So now we have to divide our total portion into two parts, this part and this part, the over consolidated part and the normally consolidated part. So this is my over consolidated part and this is my normal consolidated part. Okay, so in the over consolidated part we need to use CS, and in the normally consolidated part we need to use the CC, that is the compression index, right? So from here to here in this region we are using CS, and from here to here we are using CC. Okay, now next is if say my initial stress is here. Okay, initial stress is here, say, right, which is greater than my pre-consolidation, which is my soil is in the totally in the normally consolidated part. So if that is the case, what I have to do is that I have to use CC, only CC. Okay, so like this we have three cases, right? The first case was that my updated stress, my incremented stress is less than the pre-consolidation pressure. Okay, my second is that my incremented stress is higher than the pre-consolidation pressure, but my initial stress is lesser than the pre-consolidation pressure. So some part will be coming in the over consolidated section, some part in the normally consolidated section. And my third case is that my whole soil is my normally consolidated. That is my initial stress and my updated stress both are in the normally consolidated part. That is both of them are greater than the pre-consolidation pressure. Then we have to use CC. Okay, in this case we have to use CC. This case, this case. Now another concept is there, a concept of secondary consolidation. Okay, the secondary consolidation or secondary consolidation settlement. So that actually happens to the plastic rearrangement of the soil. So you can see, so you will get a void ratio versus time plot. So from there, what you need to do is that you need to graphically obtain this EP value. Okay, you need to draw two tangents and obtain this EP value. EP value is nothing but the void ratio at the end of my primary consolidation stage. Okay, so you need to obtain that. Okay, so graphically obtain EP. Then you have to do is that this you need to, this is my equation, right? This is my equation. So you need to use for secondary consolidation settlement equation, you actually need to use this. So it is kind of creep, you know, right? You know creep, right? Creep is nothing but time dependent deformation of because the soil or structural uh, engineering also creep happens, right? Of concrete, time dependent deformation of concrete, okay, or anything, any material, it is known as creep. So here what happens, this settlement is actually dependent upon time, not on stress. Okay, okay, so from the void ratio versus time log of time plot, what you do is that you determine EP, right? And then you determine the C alpha. The C alpha is nothing but the slope of this section of the curve, this part. Okay, the slope of this part, this part. Okay, it is a secondary. From here to here, it is actually secondary consolidation settlement. Right. So time from the time E versus log of time graph, you calculate EP, and you find the slope of this part, which will be nothing but C alpha. Now this C alpha, from C alpha you determine this C prime alpha using this relation, and then using this finally this secondary set this sorry. So finally using from this, you can actually determine the uh, secondary consolidation. So next, this was all about the settlement part. Okay. The next, uh, next we study the one-dimensional consolidation theory, which deals with the time. Now the time comes into the picture. Okay, till now only we are bothered about the settlement. It is the ultimate settlement of our soil. Now actually the time comes into the picture. Means how much, say, how much time will be required for the soil to to reach, say, 50% of my ultimate settlement. Till now all the calculations we did, all the primary consolidation settlement calculation we did, those were actually giving us the ultimate settlement value, that is a total settlement value that the soil can actually that the soil will actually undergo. Right now what will be now what will what we will be determining is that how much time is actually required for a particular amount of settlement to occur, say 60% of the total settlement, say 20% of the total settlement, to for the soil to undergo, say, that much of settlement, how much time is actually needed. So those calculations we will be doing now. So that thing is actually given by the Terzagh's one-dimensional consolidation theory. So this is the differential equation, which is very, very important, which is nothing but the consolidation, one-dimensional consolidation equation. Remember, it's one-dimensional because we just have z term here, right? Only z direction. Our flow of drainage is occurring only in one direction. We are considering only one direction. Okay, only in this vertical direction. Other directions are not considered. Right, that's why it's known as one-dimensional consolidation. And also we can see that in the uh, in our in this differential equation, in this partial differential equation, we have this z term on, right? Means it's one dimension. Now so you can see that dou u by dou t is equal to cb into dou square u by dou z square, right? So this is my one dimensional. So derivation was also it was done in detail in the class, so I won't be going into that, right? So in this equation, in this differential equation, you have this term CV. So this CV is called the coefficient of consolidation. Okay, so the particular soil, it is a constant. Okay, so the particular type of soil, it is a constant. So it is dependent on, it is equal to CV is equal to K by gamma W MB. So K is my hydraulic conductivity or the coefficient of permeability. Gamma W is the unit weight of water, and MB is the coefficient of volume compressibility, is nothing but A. So 1 plus M. This is the coefficient of consolidation. Now, what are my boundary conditions? If you see here, so this is a differential equation, right? So in order to solve this differential equation, we will be requiring some boundary conditions, right? So we will be requiring some boundary conditions. So what are the boundary conditions? Let us see. So at z equal to 0, okay, so this is our clay layer. This is our clay layer, right? So say here your condition is z. So at z equal to 0, my u will always be 0 because here we have the drainage layer, right? Just above it, just at that. So my pore water pressure will be always be 0. So this. Now second is my z equal to, just a, yeah. So what I was saying is that, yeah. So at yeah. So at z equal to 0, my pore water pressure is 0. It is at this point. So at z equal to twice HDR, my pore water pressure is 0. right? At this point, at time t equal to 0, my pore water pressure is equal to the initial pore water pressure. Okay, means at the time t equal to 0, at time t is equal to 0, this my pore water pressure actually looks like this. Okay, if this is the pore water pressure diagram, this is the u naught. At time t is equal to 0. This is the picture of the pore water pressure, initial pore water pressure. Okay, so what we use is that we use the technique of separation of variables. Okay, we use these separations of variables technique to solve this differential equation. Okay, so after solving this differential equation, we obtain this as the solution. Okay, so this is my pore water pressure. Water pressure is nothing but summation m equal to 0 to infinity 2 naught by m sin mz by twice h e to the power minus m square tv. Okay, this is the solution that we obtain. Now here are some terms. Let us see this. Just a second. Yeah. So TV is my time factor. Okay. TV here, you saw this TV, right? It's TV. So TV is my time factor. This TV is equal to CVT by HDR square, means CVT divided by the length of the drainage path. So here my depth was twice HDR. Okay, so drainage path will be half of this one because it's double drainage. The top also, bottom also, water can come out. Okay, so this one will be my drainage path. The maximum distance a water particle has to travel in order to drain out. That is nothing much that drainage path, HDR. Okay, so this is a non-dimensional time factor. Okay, this doesn't have any. So then we see degree of consolidation at any depth at z, time t is given by this. This u capital U Z is nothing but the degree of consolidation. Degree of consolidation is given by this 1 minus excess pore water pressure is time t by the initial pore water pressure. Okay, so this is the expression for the degree of consolidation. Now for this time factor, we actually have a relation between this time factor and this degree of consolidation. Okay, for this degree of consolidation between 0 to 60%, my time factor is given by this expression, and for the degree of consolidation greater than 60%, this is the expression. Okay, okay, so now let us see this plot a little bit, graph a little bit. So it is nothing but this side, it's the depth z by HDR. It's just plotted in a non-dimensional form. So 0 to 2 it's going z by HDR, and in this direction we have the degree of consolidation, right? And so we are getting various plots of this TV. TV is nothing but a time factor. Now what is the time factor? Time factor is a direct relation between time. Okay, it actually connects us to the time. This time factor is the entity which is connecting our deformation to the time. Okay, so if time factor is 0.1, means just at the start of the this consolidation process. So as we are going this direction, that means as time increases, my time factor is also increasing. Say here it's 0.9. Okay, so in this curve, you can see that the degree of consolidation is very high. Here it's 0.9. But in this curve, you can see that at this height, at mid height, say we choose a height, which is the mid height. At mid height, when the time factor is 0.1, what is my degree of consolidation? Is very less, is less than 0.1. Okay. But at the same height, when time as time passes and my time factor increases to 0.9, what is my degree of consolidation? It's close to 0.9. Okay, so as my time is actually increasing at the same layer, at the same point in the soil, my degree of consolidation is actually also increasing. Okay. So now after this, we will be solving some of the problems. Okay. So I hope all these things were clear, and these were like very nicely taught in the class also. So I hope you do not have any confusion in these things. So if there is any doubt, if any doubt comes while solving the problem, so we will be try to like solving those things also. Okay. So now let us start solving the problems one by one. Okay. So my first problem is for the soil profile shown in the figure. Initially, water table is 5 meters below ground level. Okay, which is lowered permanently to a depth of 15 meters below ground level by pumping over a few years. Okay, so initially my groundwater level, groundwater table was here. Then for many years, say water is being sucked out from the ground by pumping. Okay, so due to this prolonged pumping, what happens? The natural groundwater table actually recedes. Okay, the groundwater table is lower to this point. Now, assuming unit weight of water has 10 kilonewton per meter cube, unit weight of sand above the water table is this much. Unit weight of sand and clay below the water table is also given, and the coefficient of volume compressibility is also given. It is MB is given. So we need to determine the settlement of the clay due to the lowering of the water table. So what will happen when the if the water table lowers? Okay, what will happen? So this is my clay layer. Okay, so this is my clay layer. Okay, above that it's completely sand. Right. So what will happen if the water table comes down? What will happen to the effective stress at this point, at the midpoint of the glacier, at this point? Initially, say you had water was up above, there was some effective stress that was coming in. Now, if the water table gets lowered, what will happen to the effective stress at the same point? Will it increase or will it decrease? The effective stress is going to increase or it's going to decrease. If water table gets lowered, what is it going to happen?
Core water pressure will reduce.
No, I'm asking about the uh, this one. Okay, pore water pressure will reduce, right? So what will happen to the effective stress?
It will increase.
Yeah, it will increase, right? So due to the lowering of the water table, our effective stress will increase. So initially there was some effective stress. Due to the lowering, my effective stress will increase. So due to this increase in effective stress, what will happen is that there will be some settlement, consolidation settlement in the clay layer. Okay, so you are being asked to find out that consolidation. So let us first calculate before lowering of the water table. Uh, what is my effective stress at this point? This point before lowering. So please tell me. So my groundwater table is here. Okay, at this level. So first will be this much. This much. So 5 into
18.
5 into 18. It is unit weight of the sand above the water table plus 15 into 15 into how much?
9.
Yes.
Okay, sorry.
Yes. 20 minus 10 into
10.
10. 10. Yeah, 20 minus 10. So saturated is given as 20. 20 minus 10 will be 10. Plus 2.5 into same 20 minus 10. Because 20 is the unit weight of what the both the sand and clay below the water table. Right? So unit weights are same. So please calculate this one, how much it comes.
265.
Okay, 265 kilonewton per meter square. Next we have this. Next, after the lowering, let us find out. Will be 15 into 18 plus 5 into 10
20 plus 2.
plus 2.5 into 10. Right. So what will be the value? 15 into,
345.
yeah, 345. Okay. So what is my increase in stress? Three 45 minus 265 something back. Now to find the settlement, see, we have been given the value of coefficient of volume compressibility. Okay, so please what was the relation between settlement and volume compressibility? What was the relation between settlement and volume compressibility? Was H naught mv to this, right? So what is my H naught? It is the thickness of the clay layer. 5 into mv, it's given 25, 0.25 meganewton per meter. So 0.25, I will be converting it to kilonewton minus 3 to 80. Okay, so it will be 100 mm. Okay, so see the units and do nicely. So your settlement will be 100 mm. Okay, so due to the lowering of the water table, what happened? The effective stress increased. Due to this effective increase in effective stress, what happened? There was some consolidation settlement in our clay layer. Okay, so these problems are actually encountered sometimes. Uh, so what happens is that if there is a house, say, constructed, and beside that the groundwater table initially was very high, and then as uh, the your as the time passes, what happens is that people are using that groundwater, or what happens to some natural uh, natural conditions, the groundwater table descends, lowers, whatever there is some settlement of the soil. Okay, so now let us move to the next problem. So here, so one figure is given to us. Okay, so we are asked to find the settlement of both the clay layers. Okay, so this is one clay layer A, this is another clay layer B. So two clay layers are given to us. We are asked to find the settlement of both the clay layers. Okay, and also we can see that here our increase in stress is given to us 150 kilonewton per meter square, which is acting all over, right? So this is given to us. So we need to find the settlement of both the clay layers. Okay. So first, what we need to so first let us find for the upper layer. Okay. So for first we will find for layer A. So what is the first step here? What we have to do? See, the groundwater table is here. Okay. See, okay. Have a look in the figure properly. The groundwater table is at the top. So the unit weight of sand is saturated unit weight of sand is actually given to us. The saturated unit weight of sand is given, but no unit weight of the clay is not given to us. What we need to do is that we need to find out the submerged unit weight of this clay. So let us find that out first. Okay. So what is the formula for submerged unit weight? If you can recall, G
minus
1 by
1
1
plus
plus E to tomato. So it's given to us 2.7 1 by 1 plus E. What is C? S equal to W G. So S is 1 is equal to W into G. So so 0.4 into 9.8. So please find out the value. 2.7 minus 1 by 1 plus 1 2.7 to 9.2 will be 8.02 per. Okay, so both the clear layers are actually same. You can see same values, so it's good for us. Now let us calculate our effective stress at this AA dash AA level. Okay, this AA level. Let us calculate the effective stress. So please find out 6 into how much? 6 into 20 minus 9.81 plus 0.5 into 8.02. Nothing but 6 into t minus 9.81 73.17 per meter square. Okay, the CC value is given to us. So now we can easily calculate the settlement. So what was the formula for settlement? Settlement calculation. What was the formula for settlement calculation? CC H naught 1 plus E naught log this one. So this one. So what is my E? Let us just find it. 0.4 into 2.70, 0.08, 1.08. So it's nothing but 0.35 into 3 by 1 plus 1.08, 10, 3.17 plus 150 by 73. Answer. Please find this up. So do the calculation for this one. Let's see how much it comes. 0.35 into 3. Actually 0.2447 meters or 24 point, you can say 45 centimeters. Okay, so this much is the settlement of this A layer, clay layer, first layer. Now let us do the same for the layer B. So let us find out this effective stress first at this BB level, at this level. So 6 into 20 minus 9.81, 6 into 20 minus 9.81 plus 3 into 8.02 plus 12 into plus 12 into again 20 minus 9.8 plus 1.5 into 810. So let us see how much. Then 2.29 0.5, right? So same the same way we will be calculating the just I'm writing it again and again. So 0.35 into 3 by 219.5 plus 150 by 10.5. Okay, so if we do, the answer will come out as 11.42 centimeters. Okay, so what will be the total settlement? Total settlement is nothing but LH1 plus it is 24 point 24 plus 11.42 35.87 centimeters. Okay. Now let us come to the next problem. So here we have an odometer test is performed. That is the one-dimensional consolidation test is performed on a normally consolidated clay stratum that is 350 centimeter thick. And it is found that the clay's initial weight ratio was this much, 0.8 it's given, and its primary compression index is 0.28. Okay. So it is given to us that the soil is normally consolidated, thickness is given, initial void ratio is given, and the compression index is given also. The in situ stress is also given. Okay. And the secondary compression index is also given to us, which is 0.02. The building exerts a pressure through its mat foundation of 80 kilonewton per meter square. Okay. So there is a mat foundation. So the building is exerting this 80 kilonewton per meter square pressure at the in the soil through its foundation. The time of consolidation of the primary settlement is approximately 18 months. Okay. So what is the total consolidation of 350 centimeter clay stratum 5 years after the primary consolidation? Okay. So for the total time required for this primary settlement is actually given as 18 months. Okay. Now it is asked what is the consolidation of means how much consolidation will this soil undergo 5 years after this primary settlement. Okay. So let us see how to solve this one. So the first step in this problem is what we will do is that we will actually determine the primary consolidation. Okay. We'll determine the primary consolidation settlement. So we know the primary consolidation settlement is given by this, use this formula just now. Okay. So CC value is given to us 350 centimeters given. This is also given 120 percent by 80. So this comes out as 28 350 come out as 12.5 08 centimeter. Okay. Now let us calculate the secondary settlement. Secondary settlement, what is secondary settlement? CSH by 1 plus E100 here. So this E100 is actually the time, the void ratio at the end of my primary consolidation state. Okay, that is 100% of primary consolidation is over. That's why we are writing 100. That's E100 or T100. T100 means the time required for 100% of the primary consolidation. Right. So a secondary settlement is nothing but CS into H by 1 plus C100 log 10 T by K. Right. Now, what is my E100? E100 is nothing but initial minus this reduction in the void ratio. Right. So this E100 we can write down as E0 minus CC log this much. Right. This delta I can be written as this thing. Because it's nothing but a slope, right? So that slope we are representing CC terms this thing. From the E versus log of void ratio curve, if you remember the things from the previous lecture. So from there, we are writing this. Delta E, we are writing as this thing. So it will be nothing but 0.8. It is given minus other values you already know, 0.28 log. So it will come out as 0.73. So initially my void ratio was 0.8, but at the end of my primary consolidation, and at the end of my primary consolidation, my void ratio is this much, 0.73. Okay. So E100 I have found out. Now, what is the thickness? See, this one should be E100, H100. Means this H100 is the thickness of the clay layer after the primary consolidation. So before the primary consolidation, what was my initial thickness? 350 centimeter. Now 12.08 centimeter of settlement has occurred. So what will be the thickness of the clay layer after the primary settlement? Each 100 at 100% of the primary settlement. What will be my this? What will be my the thickness of clay layer? Is nothing but 350 minus 12.0. It's nothing but 337.92 centimeter. So I got E100, I got H100. Okay. So in 18 months, my primary consolidation is done. Right. It is given to me in the question, isn't it? In 18 months, my primary consolidation is done. Now it is being asked to us 5 years after this primary consolidation, what will be the total settlement? Means after the primary consolidation, whatever settlement that occurs, that is nothing but our secondary consolidation. So what we need to do is that we need to just add the we need to find out the amount of secondary consolidation that is occurring in this 5 years time. Okay, so we will just do this. We will just put the known values in this relation, SS relation. So what is my secondary settlement? 0.02. It is given to us in the question. The coefficient of secondary consolidation is 0.02. Sorry, the coefficient of secondary compression. The secondary compression index is as 0.02. Secondary compression index is given 0.02 into 337.92, right? By 1 plus 0.73. All those things you just now we found out. This into log T by T100. So what is my T100? Nothing but 18 months. 18 months is in years if you want to write it down, 1.5. And what is my this one? T is nothing but 5 years. So if we solve this, we will get my secondary consolidation as 2.4 centimeter. Okay. So if we compare this with 13 centimeter, this 12 centimeter is quite less. So secondary consolidation is actually very less and very slow. It's very, very slow because you can see the slope is so low, 0.02, and see the slope here. The slope is very less. So the secondary consolidation is very, very slow. It takes long time. So in 5 years, only 2 centimeters will occur. Okay. So now finally, what we do is that we find out the total settlement. It is nothing but the consolidation settlement plus the secondary, secondary. So what is my consolidation settlement? 12.08. What is my secondary settlement? 2.4. 13.12. Okay. So this is the total set. So let us look into this problem once again. So, so it was given to us that CC was given to us, everything was given to us. All the values required for us to determine the primary consolidation has been given to us. Primary settlement is given to us. Okay, CC was given to us. This increase in stress is given to us. Initial void ratio was given to us. So what we did was we determined this primary consolidation. Okay. Now it is being asked to us that this primary consolidation settlement occurs in 8 months, 18 months. Okay. This 12.08 centimeter of settlement occurs in 18 months. Now, after what we, so it's being asked to us in 5 years time, what will be the settlement that will occur? Okay. That means in 18 months, my primary consolidation will be over. The rest of the time, whatever settlement is occurring, it is nothing but our secondary settlement, right? So what we do is that we write the expression for the secondary settlement. In this expression, then we see that this CS is known to us, this T100 is known to us, it is 18 months. These other terms we need to determine. So what we next determine is E100. E100 is nothing but a void ratio at the end of the primary consolidation stage. So we know the initial void ratio, from that we deduct this because we know this thing. We found out this E100. Now, how to find this 800? 800 means the thickness of the clay layer at the end of the primary consolidation state. So, from 350, we deduct the primary consolidation, we will get the thickness. We got this 337.92. Okay. So, now we have all the values 800, we have E100, we have T100, we have T, we have nothing but 5 years. So, what we just plug in these values in the equation and we determine our secondary consolidation as 2.04 centimeter. Okay. So, my total settlement, it is the primary settlement plus the secondary settlement, comes out as 14.12 centimeters. Okay. So this was all about this secondary settlement thing. Okay. So now let us proceed to the next one. So in the next problem, it is told how many days would be required by a clay stratum 6 meter thick, okay, draining at both ends with an average value of coefficient of consolidation as this much to attain 50% of its ultimate settlement. Okay, so the thickness of clay stratum is actually given, right? The thickness of clay stratum is given, and it's given that it's draining at both ends, so double drainage. Okay, in both the this 6 centimeter, this is the clay layer 6 centimeter, and it's draining at this both these sides, both these sides. The average value of coefficient of consolidation is given by 50 to 10 to the power minus 4 cm square per second. What we need to do is that we need to determine the time required for 50% of ultimate settlement. Okay, the time required to attain 50% of its ultimate settlement. Okay. So what will be our first step? As soon as the time comes into picture, okay, time comes into the picture, what we need to find is that we need to find our time factor. Okay. So for 50%, 50% is less than 60%. So what was the relation for time factor? For degree of consolidation between 0 to 60%, nothing but pi by 4 into u by 100 square. So pi by 4 into 50 by 100 square, nothing but 0.197. Okay, so these sum values actually you should remember for 50% settlement, for 90% settlement. These things actually you should remember TV value always for faster calculation. Okay, so 50% settlement, TV value is this one, right? So now what is the relation between TV time factor and my time with TV? This one, this is the relation. What is CV? CV is nothing but the coefficient of consolidation. We have its value, it's given to us. P50 we need to determine. What is D? D is the drainage path, length of drainage path. So please tell me what is the value of D in our case? What is D?
Meter.
How much?
3 meter.
Yeah, it is 6 by 2. It is 3 meter. Okay. So T50 we have 0.197. CV we have, right? T50 we need to find out. This 3 meter means 300 centimeter square. Okay. So please solve this. Please find out the T50. Tell me how much is it coming. It will come out in seconds, right? So you can convert those seconds to days. How many days is it coming?
41.04 days.
Okay, 41.0. So in 41.04 days, this clay layer will attain 50% of its ultimate state. Okay. So you can just see, just in 40 days, it will just attain 50%. Okay. So for 100, for 90% settlement, it will take a much longer time. Okay. Let us go to the next problem. Yeah. A soil stratum is 10-meter thick with pervious stratum on top and bottom. It's again double drainage. Okay. Determine the time required for 50% concentration. Given K is equal to this much, AB this much, N is equal. Oh, please solve this one yourself, then I will solve. This one is exactly same as before. So it's very easy. Please solve this one. K is given here. K is given. AV is given. E is given. So you can find out CV, right? So please find out CV. So please find out CV with proper units. Okay, units are very important. Please find out CV. What value of gamma W shall we put here?
9.81.
No, no, 1. Everything is in centimeter and gram, right? See, this one is also given centimeter per gram, G value, this AV value. So you can directly put 1.
1 into 10 to the rest minus 3.
Okay, so 10 to the power minus 3 centimeter per second is the CV value. Okay, so now what is my D value? 10 by 2 meter. So now exactly same as before. We can find out T50 is CV T50 by T square. So T50 is CV. Please calculate. What is T50? T50 is just now we calculated 0.197. How many days? It will be quite high. What is T50? Very simple. 0.197 into 5 meters. So you can do 500 square divided by this 10 to the power minus 3. It will come in second. So please just convert that to days.
$57 days.
570. It's coming. 570 days. 0.197 into 500 square divided by CV is how much? 10 to the power minus 3. So it's a huge number. Divided by 36006 into 24. Yeah, it should be 570 days. So in 570 days, see more than a year, right? 570 days means 1 point almost 1.6 years. So in 1.6 year, this clay layer will actually undergo 50% of consolidation. Okay. Okay, so the next problem, a homogeneous clay layer 12 meter thick is expected to have an ultimate settlement of 322 millimeters. Okay, so this one is the ultimate settlement of a clay layer 12 meter. After a time span of 3 years, the average settlement was measured to be 152 millimeter. Okay, the average settlement, the layer. How much longer will it take for the average settlement to attain 237 centimeter, 237 millimeter? To take this. Okay. So tell me, what is the degree of after 3 years? What is my percentage of consolidation that has taken place? What is the degree of consolidation after 3 years? What is the degree of consolidation after 3 years?
Almost 50%.
Yeah, almost 50%. So let us find the value. So this is, let us write degree of consolidation, say U1. U1 is equal to how much? 152 divided by 322. Okay, nothing but 0.458. So, or 45%, 45.8%, almost close to 50%. Close to 50% settlement is occurred. Okay. Now we need to find out at the time t at which my degree of consolidation is this much. What much? 237 by 322. Nothing but 237 by, see, for this much, 3 years, 3 years is required, right? For 237 divided by 322 for 0.736, almost 74% settlement, we need to find out the time. Okay, so this is my question. Okay. Now for u1, okay, for this it is less than 60%. So what we will do is that we can use this relation tv1 is equal to pi by 4 into u1 square, right? So what will be my tv1? 0.458 square, but pi by 4 into 0.458 square, 0.1647, 0.165. Now let us write the relation between TV and time. So TV1, you can write CV into T1 by D square, isn't it? So 0.165, this one we just found out, equal to CV by D square into time. What is the time? Nothing but 3 years. Okay. Also, TV2 will be equal to CV into T2 by D square. Okay. Okay. So the CV by D square is actually constant, right? So from here, let us find out the CV by D square value. But 0.165 by 3 to 0.165 by 3, 0.055. So it's equal to 0.055 into T2. One thing I made a mistake, it is T2. Right? So if we know this TV2 time factor 2, we can find this T2. Now see, now this U2 is actually greater than 60%, right? So we need to use the other relation. So what was my other relation? TV2 is nothing but 1.781 log 100 minus U%. So 1.781 minus 0.933 log 100 minus 71.4. Okay. 70, not 70, 73 point, how much is it coming? 237 divided by 322, 73.6. 73.6. Okay, so find this value, minus 0.933 into log, this log is 10, 100 minus 73.6, but 0.455. Okay, so you put this here, 455. So IT2 will be 0.455 divided by 0.055 is 8.27 years. Okay. one mistake I've made here. See, this one should be 0.472. Right. Please correct this one. 0.472 is this one should be 0.175, not 165. So our values will change actually. Okay. Little bit it will gonna change. Zero 583 0.0 7.8. Okay. Okay. So for 152 settlement, it takes 3 years. For 237 settlement, it takes 7.8 years. Okay. So if we know how much time it's required for a certain amount of settlement, we can find the time required for another amount of settlement also. Okay, just by relating our degree of consolidation, using the degree of consolidation, time factor, and time. Okay, using these three things, relation between these three things between U, capital U, T, and time, you can find out any of these things. Okay. Okay, so the next question, at a given site, having a clay layer 8 meter thick with single drainage, okay, yeah, single drainage, not double drainage, uniform field was constructed, resulted in a settlement of 5 centimeter in 1 year. Okay, so in 1 year, 5 centimeter settlement has occurred, corresponding to 50% average degree of separation. Okay, okay, so in 1 year, so in time, so again, similar to the previous thing, right? So in 1 year, 5 centimeter settlement has occurred, and this 5 centimeter is actually 50% of the consolidation. So degree of consolidation is 50% at time t is equal to 1 year. It was found that a neighboring site B, the same type of clay exists, but having a different thickness. Okay, how long it will take for 50% consolidation to occur, and what will be the magnitude of settlement if the field is of the same, field of the same magnitude. Okay. Uh, So for site A, some known parameters we have, and for site B, there is an unknown parameter. So using the known parameters of site A, the soil is same in both the sites, right? So what we can do is we can determine our CV value first. So TV is CVT T square. Now my thickness is 8 meter, right? Settlement is Settlement is 5 centimeter, percent is 50%. Okay, so for 50%, this TVs we know we just calculated before 0.197. So 0.197. CV we don't know. CV we can find out. What is T? T is 1 year. 1 year, you can put 1. And what is D? What will be the D here? For the site A,
Four
what
meter.
will, how much?
4 meter.
No, no. Why 4 meter?
half of 8,
Here it's given single drainage.
single 8 meter.
Then it will be 8 meter, right? Okay. So find out CV, 0.197 into 8 square. 12.608 meter square per year. Only the unit. Okay, this is side A. Now let us go to side B. Now side B, what is it given? In side B, same clay exists, right? Now thickness is different. Thickness is now 16 meter. TV for 50% consolidation, we are being asked. So TV will be again 97. So TV is CV square 197. CV you just determine 12.608. Time I don't know. By D2 square. What is D2? D2 will be 16 meters. So please calculate D2. Just find out T2. How many years?
4 years.
Yes, 4 years. Okay. Now, it is also being asked for us to find out what? Uh, wait, just a second. Yeah. So now can you tell me if here 5 centimeter settlement is occurring? Okay. 50% consolidation here also in layer A also, in layer B, inside B also, at side B also 50% consolidation. Just the difference between A and B is that the thicknesses are different. Layer side A has 8 meter thick and side B has 16 meter thick. Now, if say in 1 year 5 centimeter is occurring, settlement is occurring for this site A, what will be the settlement that will be occurring at site B? For site A, 5 centimeter is occurring. Okay, the same soil is there in site B, just the thickness of the layer, original layer is double. Then what will be the settlement?
2.5 centimeter.
No, it will be double, right? The settlement will also get doubled, not halved, doubled. How? See, what is the settlement? It's not right. This is the settlement. So we can write this thing. We can write this stress is same. That's why it's getting cancelled out for both the layers. It is given to us in the question very clearly. Same magnitude. Field is of same magnitude. Okay. So this increase in stress is same for both the layers. So you are getting this relation. Now from here we can write del H1 you know 5. This one you need to find out 8 by sorry what 8 by 16. So it's to nothing but 10 centimeter. Okay. Okay, so this okay, so let us go to the next problem. So this, I hope this was clear. Nothing, not that complicated. It was just very simple. So just we determined from the known values at one side, we determined the CV value, and that CV value we put in the put for the second side to find out the time. Okay. Okay. The next problem, a settlement analysis is carried out for a proposed structure, indicates that 5 centimeter of settlement will occur in 5 years, and the final, so 5 centimeter is occurring at 5 years. Okay, and the final settlement is 25 centimeter. Okay, so U100 is not able to look how to write like that. Okay, so my total settlement is 25 centimeter. Okay. The computation was made on the basis of double drainage. Okay, however, subsequent boring established only single drainage condition. Calculate the final settlement at the settlement in 5 years for the change condition. Okay, so this calculation, 5 centimeter in 5 years. Okay, this was actually done considering that there is double drain, but the actual condition is in the field is that it's single drainage, not double drainage. Okay, so how to calculate? So initially for this case, what is my degree of consolidation? 5 by 25 by 0.20 means 20%. Okay. In this case, my length of drainage path is, say, T1 is equal to H by 2. Okay. Now we have TV is equal to pi by 4 into U square. So pi by 4 into 0.2 square, it will be 0.0314. Okay. Now what we can do is that we can establish a relation, we can find out CV by H square, okay, from the relation between time and TV, time factor. So time factor is CVT by D square. So this time factor, 0.0314. CV I don't know. Time, do I know the time? Yes, time I know. It's 5 years. D. So suppose the clay is of H meter thick. Okay, the clay layer is H meter thick. So if it is double drainage, it will be H by 2. H by 2 square. So please find out the value of CV by H square from here. Please calculate the value of CV by H square from this thing.
One point five seven
1.57 into 10 to the power
minus
-3. Okay, so this is the value. Now for the second case, it is asked this whole computation was based on double drainage condition, but my actual condition is of single drain. Okay, okay. So now, okay, now time is again my 5 years. It is being asked for 5 years. How much settlement will be there in 5 years? Okay. Now here actually we need to make an assumption. We make an assumption that after 5 years, my C, here it was double drainage. In double drainage, after 5 years, 20% settlement is occurring. So obviously, if it's single drainage, that degree of consolidation will be obviously less than 20% after 5 years, isn't it? Because the rate will be slower. So Here we are making a, not just like randomly, we are just not making a guess, we are making a calculated guess that in case of my double drainage system, when we consider double drainage in 5 years, 20% settlement had occurred. So obviously, when there will be single drainage in 5 years, my settlement will be obviously lesser than 20%, right? That means my settlement will be, the degree of consolidation will be lesser than 60%. So the relation which I can use is again this only. This relation I can use. This relation I can use. Now this again is equal to TB is equal to CVT by D square, right? So pi by 4 into U square is equal to CV. I don't know. T is 5. T is 5. What is D here? Now it's not H by 2, it's H. H only. So H square. CV by H square value I know. Let me write down pi by 4 into U square is equal to CV by H square I know. 1.57 into 10 to the power minus 3 into 5. So what is my U square now? U square will be 4 into 1.57 pi. Okay, so from here I can find out du. Please calculate.
Point one.
Yeah, 0.1. That means 10% settlement will occur. Right. So if my final settlement is 25 centimeter, what will be the settlement that will be actually occurring? Think back, 0.1 into 25 to 2.5. So if we consider double drainage, my settlement in 5 years was 5 centimeters. If I consider single drainage, my settlement in 5 years was half of it, that is 2.5 centimeters. Okay, so that makes a lot of difference. So if the drainage condition is doubled, my settlement is also doubled. If my drainage is half, drainage condition is reduced, then my settlement is also reduced to half. Okay. So this is the actual settlement that is occurring. Okay, next problem. A clay layer 8 meter thick is subjected to a pressure of 70 kPa. If the layer layer a double drainage and undergoes 50% consolidation in 1 year. Okay, so the layer there is double drainage and 50% consolidation occurs in 1 year. Okay, so U is equal to 50% in 1 year. Okay, and double drainage. Determine the coefficient of consolidation. If the coefficient of permeability is this much, okay, then also you need to determine the settlement in 1 year. Okay, so let us see. So what is TV square? For 50% it's 0.197, you can take 0.197. 0.197. CV I don't know. Right, CV I need to determine. What is the time? It's 1 year, because in 1 year 50% consolidation is occurring. And what is the drainage path? Double drainage, so 8 by 2. So T will be 8 by 2, 4 meters. Right, so 4 square. So CV is 0.197 into 4 square, 3.152. What is the unit here? What is the unit of CV here?
No unit.
No, CV has some unit. CV has unit. CV is not non-dimensional. It has some dimension, right? CC, all those indexes are non-dimensional. CS, those things are non-dimensional. AV, MB, CV has dimensions. Think about meter square per year. Okay. Now your CV value I have determined, right? Now also coefficient of permeability is given. This one 0.04 meter per year. Now CV, what I know the relation between CV and K. CV is nothing but K by MB into gamma W, right? So here I can, from here I can find out MB is nothing but K into CV into gamma W. Okay, so what is K? K is 0.04. What is CV? We just found it out, 3.15. So it will be 1.3 into 10 to the power minus 3 meter square per kilometer. Okay, so you have the MB. If we have the MB, we can find out the settlement. MB into this into H. If we do, we can find out the settlement. So 1.3 into 10 to the power minus 3. What is the pressure? 70 kPa. 70 into what is H? What is H? 8 meters. 8 to P 0.728. So this much is the total settlement, total consolidation settlement that my soil will undergo. Now it's asked was if the determine the settlement in 1 year. Okay, that means 50%. So 50% consolidation in 1 year. So total consolidation I determined this much. So in 1 year, what is the amount of settlement? 50% of this value, that is 0.728 divided by 2. Think about 0.364 meter, right? So very simple problem. So every drainage conditions are given, my degree of consolidation is given, my time is given. So using that, what I found out the coefficient of consolidation CV. Now using the coefficient of consolidation and my coefficient of permeability, I could determine the coefficient of volume compressibility, that is MB. Now using the coefficient of volume compressibility, I determined my ultimate settlement. Now I know that in 1 year, 50% settlement is 50% of the settlement is occurring. So 50% of 0.728 will give me the settlement in 1 year. It's nothing but 50% of 0.728, that is 0.36 meters. Okay, this much settlement will actually occur in 1 year. So the next problem, for the given arrangement, so there is a footing and there is a clay layer. Okay, footing resting upon a clay layer. So the properties of the clay layer are given, gamma is given, E is given, CC is given to you. What we need to determine is, we need to determine the settlement. See, previously what we did, we just divided the clay layer into 2 layers. Okay, we just divided it into 2 layers and determine the settlement. Now what we need to do is that you need to determine the settlement by dividing the clay in 4 layers. Okay, so what we did was we divided this clay layer in 4 layers. Okay, we divided it into 4 layers and we determined the settlement. Okay, so each layer is my 0.5 meter. Okay, So each layer is 0.5 meter. Now there is a footing. So first let us see what will be the base pressure. Actually no need to find out the base pressure. So 225 kilonewton is acting on the footing. So that is being distributed. We are considering that it is being distributed in the soil in two horizontal into one vertical this fashion. It's being distributed. Okay. So what we need to do is that first for all the layers, we need to calculate the effective stress at the middle of all these layers. Okay. So now first for layer one. So layer by layer, let us calculate. So first for layer, I will just erase this so that it gives you better clarity for calculation. Okay. So there is no water table, there is nothing, right? Nothing is, no water is not there, nothing is there. So it is more simpler. Problem is very simple. So for layer one, tell me the effective stress at the center of the layer one.
1.75.
Yes, 1.75 into 20.
20.
So 35. Now what is the delta sigma 1? Increase in pressure at this point. Increasing pressure due to the footing at this point. So you're distributing it. Right? How you can determine? You can determine this C225 turbine by 1.5 plus 2 into 0.5 square. Right? See, this one is the footing.
It
So
shall
this,
2 into 0.25. We are taking at the layer
yeah, 2 into 0.25. Right? That's why 2 into 0.5 you're writing. See here. So this one is the center. So you're telling this one is 0.25. Okay. Okay. So two horizontal to one vertical, two horizontal to one vertical. So so horizontal, what is my vertical? 0.25. So each horizontal is 2 into 0.25. So this one is 2 into 0.25. This one is 2 into 0.25. Right. So what is the total length now? 2 into 0.25 plus 1.5. Isn't it? Hmm?
right.
Right now. So your rating is 2. So for better clarity, let us write it like that. 1.5 plus 2 into 0.25. Okay, so it will be 225 plus 1.5 is 2 into 0.5 squared 36. So now you know how to find out the settlement. Five plus 36 by 35. CC it's given to you 0.07. What is H? H is 0.5 meter. What is E? E is given as 0.8. So please calculate. 7 into 0.5, 148. Calculate in mm, okay. 5.97 mm. Okay, is it coming 5.97 millimeters? Okay, similarly for layer 2, what will be the effective stress at the center of layer 2? 30, 30 35 plus 0.5 into 20, 45, isn't it? Here at this level. And what will be my this thing? 225 1.5 plus 2 into 2 into
2 into 1.
0.75, right? That's 4.1.5 plus 20. Yeah, right. Now here, see, now here it's from here to here, it's 0.75. So 1.5 2 into 2 into, so 4.5 square. So 225 divided by 4.5 square, 11.11 kilonewton per meter square. So again, using the same formula, you can find out S2. Okay, 0.07 into 0.5, 1 plus 0.8 log n, 45 plus 11.11 by 45. It will give you 1.86 mm. Okay, so similarly, I will just write all the values for layer 3. You will get S3 as 0.78 mm and layer 4 S4 as 0.39 mm. So total settlement will be S1 plus S2 plus S3 plus S4, nothing but 9 mm. Now we got 9 mm by dividing it into 4 layers. Okay, now what you can do is that you can try by just dividing this into 2 layers and check how much it's coming. Okay, we can do this now only very easily. Say just we need to determine the set. Okay, you do that one later and check. Okay, if we just divide it into 2 layers, then how much is it coming and what is the difference? Okay, you can check one. So if we divide into 4 layers, 9 mm is coming. If we divide it into 2 layers, how much is the settlement it is coming? It will be close to 9 layers, 9 mm, but it won't be same actually. It will be close, but it won't be same. Okay, so you do this one as homework. Okay, and check how much is the difference by just dividing it into 2 layers instead of 4 layers. Okay, so let us go to this problem. A saturated soil stratum 6 meter thick lies above an impervious stratum and below a pervious stratum. Okay, a saturated soil is there 6 meter thick. It lies so above it's pervious, means drainage can happen, and below it's impervious, so no drainage can happen below. Okay, so single drainage problem. It has a compression index of 0.28 and a coefficient of permeability of this much. It's given. Compression index is given, Cc is given, and K is given. Its void ratio at a stress of 150 kPa kPa is this much, 1.92, because void ratio at a stress of 150 degrees. We need to determine the change in void ratio due to an increase in stress to 210 kPa. Okay, if the stress is increased to 210 kPa, what will be my change in void ratio? Also, we need to determine settlement of the soil stratum due to the above increase in stress. Okay, due to this increase in stress from 150 to 210, what is the settlement of the soil stratum? Third, we need to find out the time required for 50% consolidation. Okay, time required for 50% consolidation we need to find. Also, the amount of settlement which will take place in 1 hour. Okay, the ultimate settlement was given as 72 centimeters. Okay, so many things we are asked to find out. So one by one, let us solve. Right. One by one, let us solve. The first thing is we need to find out the what? Change in void ratio due to increase in stress to 210. From 150, it has been increased to 210. So what? It's very simple. We will just use our this relation between CC. CC, we will use our CC to determine this. Right. So CC is nothing but change in E. Very loud. This one. So from here we can easily find out delta E. CC into log. And the CC is given to us 0.28 compression index. So 0.28 into log. Sigma 2 is 210. 210 by 150 it's given. So if I do this, it's come out as 0.041. So we just solve this. Okay. So with increase in the stress from 150 to 210, my void ratio will actually reduce by 0.041. So deducted. This is the change. Now let us go to the next problem. The next is what will be the settlement of the solid with the increase in stress. Okay, we need to find out the settlement. So you know settlement. Right? Right. So what is CC? 0.28. What is H? 6 meters. It's given 6-meter thick layer. Okay. Void ratio is also given to us 1.95. 210. So find this out. How much meters, centimeters, or millimeters? How much millimeters is it coming? How much millimeters?
0.083.
That is meters, right? So it will be 83.22 millimeters, right? 0.083 meter. So 83 millimeter. So please don't make mistakes in the units, okay? So in the exam, similar options will be there. So 0.83 will also be there, 83 will also be there, some other things also will be there. So options will be there to confuse you. So please don't make any mistakes in the unit. So next question is the time required for 50% consolidation. So we will just use this PV is equal to CVT by D square relation. So do we know the CV value? CV is not given to us directly, right? So we need to determine the CV value. So how to determine the CV value? K value is given. MV value I need to find out. Right, MV I need to find out. So for MV, I need to find out AV value, coefficient of compressibility. So first, let us find out coefficient of compressibility. AV is nothing but this by this. So what is this? You know, already determined. And what is the delta sigma? 110 minus 150. So therefore 1 divided by, so 6.83 into 10 to the power minus 4 meter square per kilonewton. Okay, so this is the AB. If this is the AB, what is the MB? AB is nothing but MB is nothing but this much. So 6.83 into 10 to the power minus 4 by 1 plus what is E naught? 1.95. So 95. So 2.32 into 10 to the power minus 4 meter square plus by K. This is my coefficient of volume compressibility. Now I have my MB, my K. I know gamma W, I can find out CV. So what is CV? What is CV? K MB
Gamma W.
gamma W. So what is K? How much is K? 3.5 into 10 to the power minus 4 centimeter per second. 3.5 into 10 to the power minus 4 centimeter per second. I convert it to meter per second. Okay. So MB is 2.32 into 10 to the power minus 4, 2.3 into 10 to the power minus 4 meters per kilonewton, and this is 9.81 kilonewton per meter cube. So if I do this thing, it will be 1.54 into 10 to the power minus 3 meters square per second. Okay, so I got the CV. Now very simple. By d square for 50%, it's 0.197. CV is 1.54 into the power minus 3. T I don't know. So let us see what is D. So it will be single drainage because here it's pervious, here it's impervious. So it will be single drainage. So D will be 6 meters only. 6 square. So my T comes out as, please find out the T. Be 1.279 hours. Okay. Now the amount of settlement which will take place in 1 hour. Okay. In 1 hour, we need to find out the amount of settlement that would take place. So let us find out the TV for T is equal to 1 hour. So C I know. Number 4. TV is equal to CV I know. You put here 1 hour means how many seconds? 3600 seconds by 6 square. If we do, what will be the TV? 1.54 into 10 to the power minus 3 into 3600, 36. So 0.154. It is less than 0.197. So less than 50% obviously. Na? So pi by 4 into u square is equal to 0.154. Find out u from here. 0.4428. Okay, that means 44% settlement will occur in 1 year, right? So in 1 year. So what will be the settlement that will be occurring? So 0.4428 into what is the ultimate settlement given? 72 centimeter is the ultimate settlement that is given in the question. To 72. 72 to 31.88 centimeter. Okay, so this one settlement the soil will undergo in 1 year. Okay. So I think I have one more problem. Just a second. Yeah. So this is also very easy problem. The coefficient of consolidation of a clay was found to be this one. So CV is given. The final consolidation for a 5 meter thick layer of clay was final ultimate settlement is also given to you. Assuming a uniform initial excess pour water pressure distributed, permeable layer to be present means both above and below the clay, right? That means double drainage. Compute the 90% time for 90% settlement and the time required for 100 mm settlement. Okay, so first we need to find out the time required for 90% primary settlement. Right, CV is given to us 0.955 mm square per minute. Now, what is the this PV for U percent is equal to 90% is actually 0.848. If we use the relation and put U equal 90%, you will get 0.848. Okay. So what we can do is we know TV is equal to CT by T square. So T I need to find out, right, for 90% element. So it's 0.848 I will put. CV I know 0.955 mm square per minute, right? Mm square per minute. So and D I know, D is, see, double drainage is considered, right? Present both above and below. Permeable layer is present both above and below, so double drainage. So 5 by 2 will D is equal to 5 by 2 is equal to 2.5 meter. 2.5 meter means 2.5 into 1000 millimeters. Why am I converting it to millimeters? Because CV is also given in millimeter square per minute. And this T I will actually get in minute. Okay, so what is my T? 0.848 into 2.5 into 1000 square divided by 9.955. Okay, so it's huge number. It's much minutes. So minutes is 5549738.22 minutes. So huge value. Okay, this much minutes. If you convert it to days, it will be 3854 days. If you convert it to years, 10.56 years. Okay, so this one is done. So we calculated. So 10.5 years will be required to reach 90% consolidation. Okay, 90% of the ultimate consolidation, 90% of primary consolidation. We will need 10 years to more than 10 years to reach that point. All right. So next it is asked to us for 100 mm settlement, how much time will be required. So for 100 mm means what percent consolidation? Let us what percent of primary consolidation? Let us find that out. So it will be nothing but 100 by 280. Ultimate settlement is given 280. So U percent will be nothing but 100 by 280. 100 by 280. So 0.3571 equal to 35.71%. I know U. Now for this one, I can find out TV. Pi by 4 into 0.3571 square. I'm using this relation because my U percent is less than 60%. So pi by 4 into 0.3571 square give you 0.10015. I got my TV. I just need to find out the time. TV is equal to CV T by D square. CV I know 0.955. 0.955 to time I need to find out. D is 2.5 into 1000 square and TV is 0.155. So T will be 0.10015 into 2.5 into 1000 square with a 0.95 this much minutes. 6554313 minutes. Okay, so if you convert this to days, divided by answer is divided by 24 into 60.
455.
Yeah, so 455 days. That means how many years? Oh, approximately 1.25 years. Okay. So for 100 settlement, it will need 1.25 years, and for 90% of the settlement, which is 90% will be 0.9 into 280. So 252 settlement, it will take more than 10 years, and for 100 settlement, it will yeah. Okay. So with this, we will end today's discussion. So I hope everything in this or everything was covered from this consolidation part. And in the next class, we will be going to the next topic after consolidation in the 8th week. So if there is any confusion, if there is any doubt in these problems which were solved today, feel free to ask or reach me anytime. So I will try to solve them again and try to solve all your doubts. All right. Okay. Thank you.
Thank you. Good night.
Good night.